All right. So, whoops, sorry about that. All right. So, um, now we know when our sediment sample or our ice core or our tree ring is actually representing. So, how do we know what it's actually telling us, though? Telling us about past climate. Well, there's a few things that these things are telling us. First, let's talk about ice cores. So, as I mentioned, embedded in each one of those layers are little tiny bubbles of atmospheric air. Well, what we can actually do, thankfully, even in really tiny bubbles, there are millions and millions and millions of molecules. So, what we can actually do is we can extract that air and then we can analyze it to tell us a lot about the chemical composition of that particular atmosphere at that particular time. That's really important because that gives us a few pieces of information. One, it tells us how carbon dioxide concentrations were like during the time. Uh, if you remember from last time, carbon dioxide concentrations are really one of the biggest things we're concerned about. Two, the other thing it can tell us is the presence of certain isotopes that can actually indicate how warm or cold it was. We can even see this on a seasonal basis. This graph I have right here actually shows an ice core for just the 1980 to 1990 period, and the presence of isotopes that corresponded with a warmer time of the year, a warmer season versus a colder season. And what this means is that each layer can tell us a lot about the temperature, the chemical composition. The thickness of the layer can tell us how wet or dry it was. Um, Also, any dust from volcanic eruptions can get trapped in there. And so all of this can tell us a lot about that particular time period. Um, so that's ice cores. Tree rings. Tree rings can also tell us a lot about a particular growing season. So the study of tree rings is called dendrochronology, and the gentleman who had the core that I was talking about earlier, the little tree ring core, his nickname is Dr. Dendro, and dendrochronology is the study of tree rings. Every tree ring represents a new growing season. Trees grow a thin new layer every single year. A thin new layer every single year between the older layer and then the bark from the previous fall and winter season. So each represents the next growing season. Now that can actually tell us a lot. The thickness of the ring can actually tell us a lot about what kind of a growing season it was. If it was a really healthy growing season, that means a season where there was a lot of light, there was ample moisture, and temperatures were ideal, you're going to have a really thick tree ring. On the other hand, if it was a really dry year, or if it was a really cloudy year, or if it was a really cold year, or an overly hot year, you're going to have a year where there wasn't a whole lot of growing. You're going to have a very, very, very thin tree ring. You're going to have a very, very, very thin tree ring. And so these tree rings can tell us a lot about each particular growing season. Now, there's one big negative about tree rings. Tree rings only represent the growing season. They do not tell us anything about the preceding or succeeding winter. So they really only tell us a lot about spring and summer. Nevertheless, that's still better than nothing. So that's what tree rings tell us. And then sediment samples. So here's the way a sediment sample works. Every single day, as I'm speaking and as you're watching this, there is what is called a sedimentary process occurring on all the hillsides, all the mountainsides, all of the beaches, everywhere. There is sediment that's actually being eroded. Now it's happening really, really, really slowly. And it's usually being made up for by tectonic and volcanic processes and other things that make up for it. So it's not something that's necessarily like the whole world's not going to go to shit tomorrow. Oops, sorry. The whole world's not going to like disappear tomorrow. But every single day, as we speak, there is sediment that is being broken up, and the sediment is then transported down into the ocean. Once it makes it to the ocean, it sinks down to the ocean floor and settles on the seafloor, settles on the ocean floor. Then guess what? The next day, more sediment comes in and it settles on top of that. Then the next day, more sediment on top of that, and more sediment on top of that, and more sediment on top of that. This process is continuously happening every single day. This process is happening. In addition to that sediment, embedded in the sediment can also be fossils of coccolithophores, small fish, phytoplankton, zooplankton, dinoflagellates, those are the things that cause red tide, all these little organisms that also get trapped in the sediment. What that actually allows us to do is that actually allows us to take a look at how the environment has changed over time. When an environment changes, the species that thrive versus the species that suffer changes as well. The species that thrive versus the species that suffer changes over time as well. One last big thing, in addition to what you see in ice cores, there's also something that you see in sediment samples, this isotope called oxygen-18. And the presence of oxygen-18 can tell us much about temperature. So these can tell us a lot about what the atmosphere was made up at the time, what the temperature was at that particular time. It can also tell us a lot about what the environment was in that particular time, what organisms are embedded in the sediment. And when we see a sudden shift in the organisms, that means there was some kind of sudden environmental change. Or a gradual shift can mean a gradual environmental change that either caused evolution to happen or it caused things to either migrate or die. There's a lot of stuff that can happen there. So let's talk about this oxygen-18 thing really quickly. So it all comes down to this thing called an isotopic ratio. So let me explain what that means. So there's this thing called heavy water. It is water that is made up of an oxygen atom that has a few extra neutrons to it. Heavy water exists naturally on the Earth system. There is heavy water on the Earth system. Well, when temperatures are really warm, that heavy water evaporates a lot easier, and we don't see it as present in sediment samples because it's evaporated out. On the other hand, when temperatures are really cold, that means that there's not as much evaporating happening, and the evaporation that is happening is only going to be focused on the the lighter water, not the heavier water, because evaporation is a temperature dependent process. You need higher temperatures for evaporation to happen. So when temperatures are cold, more of that oxygen-18 is getting left behind. And so there's this ratio that that people use comparing oxygen-18 to normal non-isotopic oxygen. But really the thing I want you to know is that when there's less oxygen-18 present, When there's less oxygen 18 present, that means a relatively warmer period. That means a period where there's less ice, less glaciers. On the other hand, when there is more oxygen 18 present, that represents a period of major glaciation. That represents a colder period. The last thing that seafloor sediments can tell us is a lot about the presence of fossilized organisms. As I mentioned, when an environment changes, organisms are going to do one of three things. They're either going to adapt, that's evolution. They're going to migrate, they're going to get the hell out of there for greener pastures. Ooh, forgive me. Or they're going to die. They're going to do one of those three things. They're either going to migrate, evolve, or die. Well, in either one of those three cases, the presence of that old original organism goes away. And a new organism, either a newly evolved organism or an organism that moved from another environment, because this is now a better environment for it, takes its place. So the extinction or the migration or the evolution of an organism can indicate a change in that environment. And then once again, we can use carbon dating and radiometric dating to say, okay, this is when this environmental change happened. And just like ice cores, these work just like the principle of superposition. The newest stuff is at the top, the oldest stuff is at the bottom. So here is a long sediment core. And as you notice, there's actually a nice banded structure in it that has a lot to do with how the chemical composition of sediment changes over time. And that can be caused by the rainfall being more acidic, or maybe the presence of a major volcanic eruption, or an oxidation event. There's all kinds of things that can change the color of the sediment. But the good news, or the bad news there is that unlike with ice cores, the changes in the colors don't necessarily represent a year. The changes in the colors, the changes in the chemical composition of the sediment ends up being something that could happen a lot more randomly. So that's why we still have to rely on carbon dating and radiometric dating for looking back into the past. But that being said, simply looking at what little organisms are embedded in the fossils, or sorry, are embedded in these layers, tell us a lot about past environments. So for example, I'm not going to pretend to name these different things. These just each represent 5 different species. And in the older sediment, you have these 2 different species down here. And then eventually something changes in the environment, and these 2 older species go away, and newer species come in and take their place. Well, this time where the baton was passed, where we went from the 2 older species at the bottom to the 3 newer species at the top, represents some kind of change in the environment. Now, what caused that change in the environment? That's where we start looking at ice core data to see if maybe there was volcanic ash present, or any kind of evidence of an asteroid impact using geological data and looking for craters, any kind of major dying event, any kind of major dramatic climate shift. But then using that, combining that with the isotopic ratios, the oxygen 18, combining that with looking at the composition of the atmosphere, the presence of any volcanic ash, and then other geologic data, we can actually put together a pretty good picture of our past. Now, the one thing I'll mention really quickly is that I really have only talked up to this point about these 3 proxies. But this isn't all that we have. There are other proxies that we have that could be talked about in an entire paleoclimatology course. There's a lot of other stuff that can be covered. But obviously, since this isn't a paleoclimatology course, I just need to talk briefly about the main things. But I just want to give a little shout out to the other things too. Um, Other methods include pollen. Pollen, when it's released, that represents a growing season, and we can actually look at the amount and the types of pollen that are present beneath the surface of the earth. Ancient documents. So even though we've only been taking accurate temperature records since the 1880s, there have been ancient documents that have been written for millennia. And we can actually use those ancient documents, eyewitnesses, natural disasters, droughts, famines, wars, major volcanic eruptions, and all that kind of stuff, to look back at major historical events that could have had an implication on climate. There's also the study of corals. When a volcanic island begins to sink, corals begin to build up on its exterior, and the thickness of the corals and what they're made up of can tell us a lot about that environment. Geologic evidence of sand dunes, fossils. There are instances where there are actually large marine animals that were found in deserts. That is a good sign of what's called continental drift and tectonic shift. Coal beds, water levels, and all these other things, when combined with those paleoclimate proxies, can actually give us a really good sense of what was happening at a particular time. And then more recent observations. We can actually use current temperature data to calibrate all of this, to look to see, okay, well, this is the current isotopic ratio in the ice, and that's this particular temperature. Okay, last year was a little bit lower. And then last year was also a little bit hotter. So we can do that to verify, and to also provide current observations, obviously. So once we put all of these things together, we actually have a really good reconstruction of our planet's history. We're going to talk about that in the next video.